Hello everyone. Let's continue our discussion on SVMs. In the last few videos, we looked at how to construct an optimization problem for SVMs, and then we looked at how to optimize for W and B, solve for them using the Lagrangian, and substitute back to get a form. Now we are going to continue that discussion and look at regularization in SVMs. And regularization helps in making the model suitable for outliers, and also regularization helps in avoiding overfitting. So we have seen regularization before when we looked at logistic regression. So we are going to see regularization again in the context of SVMs. So it's often used for overfitting. That is the sole motive for using regularization. But here in SVMs, it also serves an additional purpose where it can help with outliers and not make the model fit to outliers, which would not be ideal and which would make the model less efficient at test time. So we'll look at what that means. So let's see we have two graphs here, and one of them we have points all in this region, the circles, and we have all the crosses in this region, right? Suppose we have another data point come in, and that data point is very far from all the other dots or the ones indicated inside the red circle. So suppose it is here. So we can see that this point is away from these other points, quite a distance away, so it's not really fitting to the general pattern that all these other points have. And this point may not be a legitimate point, in that it might be a noisy data example which was just recorded by mistake. So its value is not really relevant for the construction of our model. But you can see here that this point actually is closer to the line, right? Which means that this point will serve as the support vector, which means the point will influence the placement of our model, our line, and which is something to worry here, right? Because this is going to shift our line and make our line less than ideal. And if that point is not a legitimate point, then we are not going to get a good model. We are going to get a less than ideal model at test time. So that's why we need to be careful of these points, and regularization in SVM helps in adjusting the model and making it ignore such points by relaxing it, instead of having this very strict margin that we came up with in the first derivation. We are going to relax the margin a little bit, and then we are going to derive it again so that such points don't affect the placement of the line. So our goal here is twofold: extend the algorithm to work for the non-linearly separable data sets. So this also helps in addressing that important problem. So for example, there is a point, let's say there's a point cross here. Now we know that this cross may not be rightly recorded because all the crosses are on the other side, right? There's one which is really amidst all these circles, so maybe it is a circle, but we are not sure. So we have this data point, and we want our model to be less sensitive to these points. So by outliers, it could be either, right? It could be ones that are on the right side but are influencing the line way too much, more than what they should, like this one. It could be this, or it could also be that they are in the wrong place, wrong side of the line, and hence making the data not linearly separable. So this point right here, right, this point is making this data not linearly separable, right? Because there is a cross that's right in the middle of the circle. There is no line which can separate the dots, the circles, and the crosses in such a data set. So this placement of this cross amidst the circles makes the data not linearly separable. So our extension covers all these points. So our extension of SVMs using regularization covers, makes the algorithm less sensitive to outliers, extends it to work for non-linearly separable data sets, and in general also helps with overfitting, right? So all these things are accomplished by this modification. All right, so now let's look at the problem. So we have a min over a distance, which we already know, this distance. And to that, we are adding this term here. So this term is for allowing some of the data points to have an additional distance, have a functional margin of 1 minus psi. So this quantity here is pronounced psi. So a psi amount of leeway we are giving some of the data points, which means the functional margin of those data points will reduce by psi. So the functional margin becomes 1 minus psi I for the ith data point. So when we do that, we are adding a cost that is equal to psi I to our optimization problem. So we want to minimize the amount of slack that we give, right? The amount of slack is given. So what is the amount of slack here? The amount of slack that we give is equal to psi I. The amount of slack is psi I, right? And how many points are there? I equal to 1 to m. So the psi I value could be 0 or could be greater than 0. So which means for points where there is no slack, we say that psi I is equal to 0. For points where we allow some slack, we say the slack is greater than 0. And we want to minimize the total amount of slack. So that's why we minimize the distance along with the total amount of slack, which is given by sigma I equal to 1 to m psi I. So psi I, each psi I gives us the slack. So it could be 0, which means there is no slack. It could be greater than 0 for some points where we allow some slack. So the total slack we want to minimize. So C here, C is our coefficient of the sum of the slack, right? So this variable gives us the amount of weight we are okay with giving to this slack. So if we have a higher value of C, then our slack, we are minimizing this entire quantity, right? So we only will allow less slack. If we have a low value of C, then we are prepared to allow more slack because this entire quantity is what we are trying to minimize. So it's sort of like our coefficient when we update regularization coefficient, which we have lambda, which we add to the weights, right? So it's similar to that. C is very similar to that. It serves as a coefficient for our slack variable. All right, so now this version of SVM is called L1 SVM. And it's not to be confused with L1 regularization, though it's also a form of regularization. So it is just called L1 SVM, where we have this notion of a slack variable and some data points having a functional margin of less than 1 or 1 minus the amount of slack. Right? So this is for some of the points, the functional margin is less than 1 and it becomes 1 minus the amount of slack that we are allowing for that data point. Okay, so now let's continue the derivation. So we have the Lagrange here. Now we are going to construct the Lagrange now based on our new constraints as well. So we have the original half W square, which we are writing as W transpose W, plus C times sigma over psi, which is our total slack along with the slack coefficient. And then we also have our original inequality constraint, alpha I, and instead of 1 it was minus 1, right? Instead of 1 we have our new margin, which is 1 plus epsilon I, and then we have the inequality constraint of the slack being greater than or equal to 0. So this is the inequality constraint for the slack. Right? So we have the original one. I'm just repeating this so we are clear. The original distance we are optimizing, right? And then this is the total amount of slack. We want to minimize that. So that's a term, the second term. In the third term, this is where the confusion usually arises. We have alpha I, which is our Lagrange multiplier for the inequality constraint. So remember, the inequality constraint had no slack variable, but now we have a new margin. And when we have a new margin with the slack, so for all points we have a new margin, except that for some points psi I can be equal to 0. For some other points psi I is greater than 0, right? So this is no slack, and for this there is some slack, which means that for these points, for the first set of points marked by the blue star, they are same as what we had before. For those points, our functional margin is still 1 and there is no change. But now there are new sets of points which are marked by yellow. For these, the functional margin is less than 1 or 1 minus psi I. So when we substitute that here, we have a minus in front, right? So we get this entire quantity here as our new margin. So that's why we have a new margin equation, inequality equation, and we have the Lagrange multiplier to go with that, alpha I. And we have another extra constraint where psi I is greater than or equal to 0, right? It's a distance, it's a positive quantity, so it's either greater than 0 or equal to 0. So now for that constraint, we have this last term here. This last term is for that inequality constraint. where alpha I and Ri are Lagrange multipliers. So now we have constructed the Lagrange for this problem. It's similar to what we did before, so except that the constraints have changed a little bit and there's another new constraint added here. All right, so now we know the drill. We have W, B, and psi alpha R, right? So W, B, psi, alpha R are all the variables we have, and we have to solve for all of them, partially differentiating with respect to each of these and setting that equal to 0. We solve, and then we get some values. Then we'll see what happens, right? So now we solve for W, B, and psi first. And then we solve for alpha and R in the next step. So that's how we have done in the past too, right? So we only solve for W and B. So now we are solving here for W and B and psi. And that is now giving us, first when we differentiate this, so I'm going to actually erase this a little bit so we can see the equations. All right, so now we differentiate this with respect to W. This first term here, when we differentiate, we just get W, right? So it's square, so it's 2W, and crosses out and we get W. This term does not have any W, so it's a constant. It goes away in the differentiation. And in this term, there is only one part which has W, which is this one, alpha I yi W transpose xi. And the coefficient of W is what we return here, nothing but minus sigma equal to 1 to m alpha I yi xi. And rest of the terms don't have W. And to solving for this, we get the same value for W, no change at all. Now, with respect to B, again, we can see that the term that has B is largely unaffected and no other terms have B, right? So this term does not have B, no B, no B, no B in this part, and no B here either, right? So we get the same thing when we differentiate with respect to B, alpha I yi equal to 0. Sigma over alpha I yi equal to 0. And then we differentiate with respect to psi of k. And when we do that, we can see this is the new differentiation we have added now for the non-separable case with the regularization term, right? And now we can see that there is this term here which has psi I, right? So this term has psi I, and then this term has psi I, and there is also this term alpha I psi I, right? So we get the coefficient of psi I here, which is, just to avoid confusion, I'm calling that psi k. So we get the coefficient of psi k, which is nothing but c. So we get, for the first term, we get c, and for the second term, that is alpha I psi I, we get alpha I or alpha k, because we are considering psi k minus alpha k. And then we get minus rk in the third term, right? So now when we look at this closely, we know that because rk is a Lagrange multiplier, we know that rk is greater than or equal to 0, because rk is a Lagrange multiplier. It should be greater than or equal to 0. And C minus alpha k greater than 0 equal to 0, which means alpha I less than or equal to C. So now all we have is another constraint added to this problem. So we already know that alpha I is also a Lagrange multiplier. So this alpha I should be greater than or equal to 0. We know that. Just by virtue of it being a Lagrange multiplier, we know that it's greater than or equal to 0. And now we have another constraint added where alpha I is less than or equal to C. So now we know that alpha I is bounded by 0 and C. So that's what we get when we add this other new slack variable and derive for the regularized or non-separable case when we make the derivations and also include this psi I, we get another constraint which is on alpha, on the Lagrange multiplier, and bounds it between 0 and capital C, which is the coefficient of our sum of the slack that we added to our our distance, right? So now our new problem becomes this. So now we had two steps to the problem, right? So first step was minimizing with respect to WB and now also psi I. So we had minimizing Lagrange with respect to WB and psi I, and then maximize with respect to alpha. So this is what we are solving. So we solved this part here. This we solved, and now we have to solve the second part, maximizing with respect to alpha. So to do that, whatever solution we got for WB and whatever things we got when we solve for WB and psi, we substitute that back into the Lagrange to get an expression. So that is what we are doing to get this expression. Remember, we got that expression. That's when we called out the kernel and we constructed that expression, right? So that expression, now think about it, it is not going to change because nothing else was added except for the fact that there is a bound now, upper bound now for alpha I. So when we completed all the psi I derivations, we only got this additional part here, which was not there, right? So when you can compare it with the previous derivation and when we substitute it back, and then you will see that the only change is this guy here, alpha I less than or equal to C. So now we got the same expression here. We have the kernel right here, and then we have this additional constraint, and we also have this which we got when differentiating with respect to B, right? So this we got when we differentiated with respect to psi I, right? So we substituted everything back and we got an expression for this second part here, maximizing with respect to alpha. So this is our second part of our optimization problem. So there are two parts to it. We only solved the first part. So we first solved the first part without psi and we got the expression. Now we solved it in this video with psi and then we get an expression. And in the next video, we will see how to solve this part here, which we call the dual. So this is, remember, this is the dual and this is the primal, right? So we have solved the first part and then we are going to solve the second part and using our algorithm. As before, we use W in terms of alpha i's. Adding the regularization, the only change that we get is the upper bound to alpha I.